Hi, guys. Just making sure things are in focus. Let's just give it a minute, see who else is going to be here.
Good morning.
How are you? A nice fall day. Did you guys have a good weekend?
Yeah, something like that.
Okay.
It was okay.
Yeah.
How about you?
Oh, you know, my weekend was nice. Thank you. I actually did a lot of grading. I have 3 classes this semester, so I was trying to catch up on my grading, and I'm still not there, as you guys know, but I'm gradually working my way through it. Would have been a pile equivalent to this big, you know, so I'm just kind of gradually trying to get there. But, you know, it was good otherwise. We, I believe, have a quiz on Thursday. Just wanted to throw you guys attention to it. Also, I wanted to, so let's write that down. So we have a quiz on Thursday. And that's just chapter 2.2. Okay. Remember how we break things up, but then that also means that our homework for chapter 2.2 is due also Thursday. I'll make it at midnight, so you guys can get that in midnight, and then whatever classwork for chapter 2.2, we'll make that due also on Thursday. So Thursday's got some stuff coming down the pipeline there. When we're in person, it's a little bit easier for me to do this, to talk about the project. Don't forget, our project is due at the end of the semester, right? So that's going to be due December, I think, is it 5th? I think the last day of our classes. Last day of classes. But we have an intermediate goal that we need to do. I need some kind of like a project description. It's non-binding, but I need you guys to be thinking about what you might want to work on and who you might want to work with too. If there's somebody in the class, you can send them, you know, an email or something like that and see if they want to work together. So it's due December 5th, but I think this Monday, I set it up to be, I don't know if I set it up on Thursday or Monday, but we'll make it Monday. So in a week from today, you want like a description. And then who's also in your group. Okay, so it's just a few sentences. And like I said before, when we talked about this, that was non-binding. I also wanted to talk about, we have a problem set. We have a second problem set that normally when we start chapter 2, I'm able to just give out copies of the problem set. It's listed on our syllabus, but I forgot to mention it last week. But the problem set, this is already up on our modules page under problem sets, and that's going to be due basically when we take our second exam. Our second exam. So keep that in mind. I'll actually set up an assignment for that if I haven't already done so, because it's at the top. It's in its own little module for problem sets, but I just want to call your attention to it because it's not being listed on our weekly modules, right? And it seems kind of unfair to, you know, throw it out there a couple weeks ahead of time for when we finish chapter 2. That'll be, you know, sometime in November. Essentially, we'll take our second exam. But you want to be able to kind of think about that. So our second problem set, I'll set up an assignment, so it'll kind of be there reminding you that you need to do that. But that's there online already. So a bunch of stuff coming due on Thursday, something due on Monday, which is brief project description, a few sentences, and then who you were working with, if anyone, and then just calling your attention to our next problem set. Now remember, problem sets count as its own separate grade, but you guys are free to ask me questions about it. You know, during class, you know, when we do our review periods during office hours, problem sets are not, I don't give solutions ahead of time because I want the slightly more complex problems. I want you to try to work it through. You can absolutely talk to other people. It's not like a quiz where you're doing your own individual work. Although you have to pass in your own work so I can grade you individually, but you can absolutely ask questions about it, you know, during class. Just give me fair warning so I can make sure that you know, I have my my answers ahead of time I can look at. Anyway, so keep that in mind. Okay, some stuff coming up. So last time last time we met, we were in the middle of 2.3 doing some really exciting stuff. So this is the lecture examples for 2.3, example 8, and example 9 is actually applying it. So remember in chapter 2, what's the neat thing about chapter 2 is that we're talking about taking stuff, whether it's, a center point of a circle or, maybe vector points, 2 points on a line, something like that. We're going to talk about, like rotating them around, say another line or reflecting them across a line, projecting them. We want to be able to talk about how do we do these transformations so that when you actually go to do these things on your game, the math is consistent with how things work in like the real world, right? And so we're talking about one of the ways to actually do transformations that's really nice and elegant is using matrix multiplication matrix properties in order to affect these transformations, right? And one of the nice things about matrices too is that I can encapsulate functionality. I can encapsulate an algorithm, right? So I can find a matrix for transformation around this line, right? This is an axis line, say for example, and I want to be able to reflect around it or something. And so I can have a subroutine that takes as input the item that I want to reflect or rotate, multiply it by the matrix in the subroutine, and then pass back the new coordinate, the thing that has been reflected, has this the new coordinate of the transformation. So that's what we're talking about here. So matrices are a nice, elegant way of doing that. We're just using multiplication and addition when we do matrices. So it's a pretty cheap, computational thing that we're working on. All right, so I'm going to finish up chapter 2.3, and then we'll just start a little bit talking about chapter 2.4. A little bit. We have the whole week to work through chapter 2.4. So I'm going to talk for just a little bit about 2.4, and then we'll stop and we'll take a look at some classwork. I have classwork problems for 2.3. They also combine the classwork for 2.3 is this page here. And then the 2.4 part is our second question on the second page. So we'll just kind of start working through these problems here so that we can see how this stuff gets applied. I posted the lecture examples that we had done before, just the 2.3 part 1. I'll post the rest of them today. So we'll call this part 2.
Miss Wilson.
Yeah.
I don't know if this will help, but for like the future, I was wondering if like it would be cool to see like this class like actually like applied the mechanics that we're learning to like an actual game engine.
I know
it helps visualization to see where all this stuff actually goes instead of just learning like the raw input.
I agree. It's funny, my background is computer engineering, and so like I can certainly code up stuff and work it through, and you guys can do it too. I actually asked the math department about that a couple years ago, and asked if we could actually do like hands-on actual coding stuff. So you'll get a chance to maybe, if you want to, do the coding in your project. But the project is about like the math, and if you want to do coding, you can. I think problem set 2, you can do some coding too if you want. But I asked the math department if we could incorporate coding in this as well, because this is a math fundamentals for games. A lot of you are coming in from either computer science or from game design, media design, and I was told that we need to focus on the math. So it is something that I thought would be neat too. I try to incorporate it as much as I can, right? So there's like a bonus question on the second problem set, which is if you wanted to code it up, you can. You just have to give me your source code, and then I can give you bonus points for it. The project has bonus points if you do coding on that as well. But because I can't require coding, then I can only offer it as bonus. But I agree. I think it'd be fun to actually do it, and maybe we can do math fundamentals for games part 2, where we actually code things up and see how things work.
That'd be cool.
I think that would be a really neat class. It's it's not something I'm authorized to do in this class, however. So, and it is something I asked. I thought, like you, I thought that would be pretty cool, but they said, no, this is a math class. So that's where we're at. But yep, great minds think alike. I was there too. Anyway, so let's go back. I'm going to see the lecture examples for chapter 2.3, and I'm looking at example 10. Now, I'm kind of using this lecture example packet. It's actually containing a lot of lecture notes, right? So if you're not following along, you're having a hard time, definitely, print these out or take a look at them online, because this is actually where a lot of the lecture notes are. So like example 10 is like a lecture note, and example 11 is taking this idea from example 10 and actually applying it, doing the math out on it. So so this one here in example 10, right, we want to figure out what's the matrix for projecting onto a line. And this line is at an angle, a specific angle to the x-axis. This is something that we're going to do actually in our classwork for chapter 2-3. So let's take a look. How do we actually do that? So let me draw that out so I can conceive what that looks like. Here's my x-axis, here's my y, and then I've got a line equation. So here's my line. So we have been so far writing our line equations as t, like some parameter t times v. V is our vector that's parallel to the line. Now we're going to start thinking about our line equations, right? The point that it's going through is the origin, so I don't have to include that x naught point anymore because it's 0, 0. But now I'm going to start calling this line all real numbers times my vector, right? So this is, but I'm going to say this is like it's making an angle theta with the axis. But this line here, right, is my my all real numbers, and it's being multiplied by some, vector here. But this is forming angle theta with the x-axis. Okay, so like when we talked about when we have like the line y equals x, for example, right? So that it's formed when I plot out 1, 1, whatever. We're going to actually do that right down here in this example here. We're going to be able to calculate what angle that is with the axis. Okay, so now I want to project onto this line. Okay, so here's the point that I have. And then here is the projection of point X, and we'll call this like, we'll put a little bar onto our line, right? And then I just want to call attention, I'm going to draw it in a slightly different color. So this is, I'm projecting onto the line, and then here's the reflected. So here's my X. Here's the point that's reflected across this line. So this is point reflected across the line. Now I'm doing this, I'm talking about the reflected point for a reason, because we just went through that, right? We did that in an earlier exam. So what's the reflection across this line? So we already have an algorithm in a matrix. We already went through, we derived the whole matrix for reflecting across a line that's making an angle with an axis. So if I have that already, I can exploit this property here. So I can exploit the fact that I already have an algorithm for finding a reflection across the line to find out what my projection is. And I'm going to tell you that right now. So the projection is the midpoint between my point that I want to project and the reflected point. Okay, so I'll call this reflected point REF of theta. REF theta. We call it REF theta because we're reflecting it across a line that's making an angle theta with the axis. Okay, that's where all these little names are coming from. Okay, so let's write that out in math. So it's going to look like the projection of X onto this line equals 1/2 the point that I want to project plus the reflection across that theta, right? It's the midpoint. That means I add these 2 points together, divide it by 2 to get the middle of that distance right there, okay? So now, right, if I want to be able to actually solve through, this is reflection, and I'm going to multiply that reflection times X, right? So this is the projection of X onto something. This is my X plus the reflection. This is my matrix times my input, right? So I can factor out, I'm gonna get 1/2, I'm gonna get X. This, when I factor out, I can't like just write 1 anymore because this is an actual like number set. So I'm gonna write the identity, okay, plus, and now I just have this matrix. And this is the projection onto X. So now I have a projection. Watch what I'm going to do. I'm going to be really sneaky here. And this is projection. I'm multiplying it. And I'm going to cancel the X values. So now this is really brilliant because now what happens is I now have a matrix for projection that's independent of the thing I want to project. So I want to project X onto this line. This right here, projection is 1/2 the identity plus reflection matrix. This is just going to be a matrix that is about the line, our theta, right? And not about the point X. And that's important because you know why? Today I want to do X, tomorrow I want to do a different one. Tomorrow the day after I want to do different, I want to do different, right? So now if I just have a matrix that talks about how do I find a projection onto this line, and it's independent of the input values, that means I can write an algorithm or a subroutine or however you want to think about an engine that's going to be taking as input the thing I want to project. It's going to do this work, and it's going to give me as output the coordinates of the corresponding point, the projected point on that line. So I've taken it out of context. I can come up with just this matrix and I can use it over and over and over again for all sorts of different input. So it's really important because we want to get things that are going to be sort of generic that I can then use over and over again, right? So I've got this line, right? And then I want to be able to project all these points onto this line. So I just want a matrix that has to do with just that line only. All right, so let's fill in the blanks about what this projection matrix is. So the projection matrix is 1/2. So my identity matrix in a 2x2 world, right? It's this is an R2. So we're in second dimension because I just have X and Y. So I've got 1, 0, 0, 1. This is my X, this is my Y, plus this one here, ref theta, reflection across theta, comes from right here, right? This, sorry, you can't see that. This right here. This is what we derived last time, right? So I'm going to fill that in. So that's going to be cosine of 2 theta, sine of 2 theta. Oh, I ran out of space. Sine of 2 theta minus, oops, cosine of 2 theta. Okay, and I'm just going to add those together, right? So this is going to look like 1/2 times 1 plus cosine 2 theta, 0 plus sine, 0 plus sine, 1 minus cosine. And this is my projection. This is the projection matrix. Okay. And all it depends on is the angle that this line is making with the axis, which I can figure out ahead of time. I can come up with this matrix, and then I can call this matrix as many times as I want to project the point 2, 3. I can project the point minus 5, 7. I can project the point, pick a point, okay, onto this line. All right, so give you a chance to finish writing that, and then we'll actually apply it. All right, so what I want to do is, let's actually plot this out. Okay, so I've got the line y equals x. So that means where x and y are equal to each other. Oh, I'm not trying this very well. Y equals x. Okay, and it's making this angle theta with our axis. That's my line y equals x. The point 2, 3, 2, 3. I want to project that onto this line. Well, I can get a ruler. I don't know. What am I going to do? So, right, I have to figure out what's my theta. Okay, so we kind of did this a little bit before, right? So I think, yeah, we did this right here on this example number 9. We had the line y equals x, and we needed to figure out what angle that was. So we kind of zoomed way in, right? So on y equals x, that means I've gone out 2 in the x direction and up 2 in the y direction, right? You know, your tangent's your easiest function because this is your opposite over adjacent. So this here, my angle is 45 degrees. So I figured it out last time, so I'm not going to rederive it. So my theta 45 degrees. And I'll write down example 9. You can see that. I think in our homework we're given, yeah, we have like a question number 2 is using a different angle measure. So that'll give us a chance to kind of see what things look like. Okay, so what I need to do is take this equation here. So I'm going to go 1/2 1 plus cosine of 2 times 45 degrees. Sine of 45 degrees. You can do this in radians too if you want. I stayed in degrees. 2 times 45 degrees. Make sure your calculator is set to degrees if you're going to do that. 1 minus cosine of 2 times 45. And I'm going to apply that to the point 2, 3. So the first thing I'm going to do is I'm going to figure out what's this matrix here, right? And then I'm going to multiply through. So 1/2. So I plug this in. This is 2 times 45 is 90 degrees. The cosine of 90 is equal to 0. 1 plus 0 is equal to 1. So this is, I'm sorry, there's a 2 in there. 2 times 45. Sine of 90 degrees is equal to 1. Sine of 90 is equal to 1. 1 minus 0 is equal to 1. The 1/2 is just a scalar multiplier. I can just multiply that later. So I'm going to go 1/2 times. So remember our matrix multiplication, right? So this is a 2 by 2. This is a 2 by 1. The inner dimensions agree. So my answer is going to be a 2 by 1. So I'm going to go 1 times 2 plus 1 times 3. 1 times 2 plus 1 times 3. So I get 1/2 times 5, 5, which is going to give me 2.5, 2.5. This is our point. This is our projected point on the line y equals x. It should make sense. Y equals x. Look, y and x are equal to each other. If it doesn't make sense, then you probably made a math mistake. So let's see. So 2.5, 2.5. Oh, it's roughly right in the right ballpark of where I expected it to be. So I'll write that down in red. This is 2.5, 2.5. Okay. But this here, right? 1/2 times 1, 1, 1, 1 is my matrix for projecting onto this line y equals x. If I said, later, I want to project the point 10, negative 10 onto this line, right? So I would have to take 10, negative 10, 10, negative, I'd be multiplying it by all of this, and I would find out what's the point on that line that's going to correspond to, or 10, negative 10 projects onto the line, okay? So this projection matrix, 1/2 times this, can be applied to any point because it's related to the line itself. And that's an important concept. Okay. Give you guys a chance to finish writing that. And then we'll do one more thing with chapter 2.3. And then maybe we'll work through the classwork for 2.3, the questions 1, 2, 3, 4. And then we'll start 2.4 on Wednesday. We'll see how things go. I want to do some problems. Okay. You guys all have this okay? All right, so we've got a couple other things that we want to think about. Example 12 says, what does the scaling map 2, 0, 0, 1/2 do? So a scaling map, let's talk about a scaling map. Will expand and contract, okay? Scaling map S will expand and contract or contract, right? It's a scalar multiple, right? We're scaling our values, right? So it'll expand it if it's greater than 1, it'll contract it if it's less than 1. Okay, so if I do this, right? So what this does is it expands by 2 in the x direction, and it contracts by 1/2 in the y direction. Okay, so for example, if I did s of we'll call it 3 and 5, right? And I wanted to apply the scaling map to the 0.35. So what that's going to look like is if I go 2, 0, 0, 1/2 times 3, 5. Okay, so my matrix multiplication, right? So this is a 2 by 2. This is a 2 by 1. Inner dimensions agree. So my answer will be in a 2 by 1. It's a coordinate, right? So now what I'm going to do is first row, first column. So I'm going to go 2 times 3 plus 0 times 5. This is 0 times 3 plus 1/2 times 5. See how it's expanding by 2 in the x direction? It's not affecting the y. And it's contracting in the y direction, but not affecting the x. This is going to be 6.5. Okay. It's our scaling map. We kind of think about it like, you know, if I've got some kind of a shape that's going to be changing, right? You know, it's going to be doubling each time. Say, for example, like if I imagine, right, if I've got a like a werewolf footprint, right, I'm going to be doing this, right? But as the footprint, as the person transforms into a werewolf, the footprint gets bigger and bigger and bigger at each, you know, step it's taking. Okay. This wasn't on here, but I'm just going to put it on here as our lecture notes too. But there's something called a left cross product, which we're going to use in the later chapters of chapter 2, like at the end. We're going to come back to the left cross product. This is a by vector A, B, C. So the left cross product that we do it's a linear map. So basically, if I'm going to go, it looks like this. I'm just throwing this out here now. We're going to use the left cross product later. And I'm going to go X, Y, Z. It's for 3-dimensional rotations. BZ minus CY. C, Y minus BZ. Okay. That's how we think about it. But this is something that's going to come up in, I think like chapter 2.7, maybe. This is rotations in 3 dimensions. That's at the end of this whole chapter. So don't worry about it. I'm throwing it out here so you have it, so you know what it is, so it doesn't take you by surprise. Okay. All right, so I think what I'd like to do actually is maybe work through some classwork problems for chapter 2.3, and then we'll come, if we have time at the end, I'll start chapter 2.4. Get my notes here. Start working through. I'm going to start taking a look at this page here, which is it says on the inside 2.4, but on our you know, on our website it says 2.3 and 2.4. And all right, so I'm just going to work through these problems. You guys are welcome to work through them also. I suggest working through them at the same time. And you can ask me questions about it, you know, if you want, as we go. We're reusing the same line that we had before.
Miss Wilson.
Yeah, what's up?
I think I missed this, but why is theta always 45 degrees? I
It's
missed
not,
this.
it's not always 45. It's only 45 in this example. Let me,
Oh, I think I seen you do another example when we are going through the
yeah, so let's pretend, so let's say if I go y equals 3 times x, right?
yeah.
So 1, 2, 3, 5, 7, 8, 9. So when x equals 0, y equals 0. So I'm going to go x, y table. X equals 0, y equals 0. When x equals 1, y equals 3 times 1. When x equals 2, y equals 6, right? And then the same thing, -1 is -3, -2 is -6, right? 3 there, and then, right, so our line, oops, oh, it should be a straight line. Sorry, I'm not a really good artist here. There. Okay, so then this angle is theta, right? So to come up with the theta, I have to look at what are my values. So I've got, right, so I'm going to zoom into there. So it's going to look like this. 1, 2, 3, and then 1. And then here's my theta. Okay, so this is my line, right? It's going off like this, but I'm trying to figure out what my theta is. So I've gone out 1 in the x direction, and I've gone up 3 in the y, and I need to figure out what theta is. So theta, if I go tangent of theta, is opposite over adjacent. We talked about the right angle trig stuff back in chapter 1, kind of as a review. So my tangent of theta opposite is 3, my adjacent is 1, right? So my tangent of theta equals 3. So to get theta, I go inverse tangent of 3. So I usually make sure I'm gonna make sure I'm in degrees so we can visualize it. So I'm gonna go inverse tangent of 3. My theta is 71.56 degrees. Right? So now that I have my theta, when I go to do like the projection matrix, I would say 1 plus 2 times cosine, 1 plus cosine of 2 times theta. So then my theta now is 71.56 degrees. So it'll be cosine of 2 times 71.56. So do you see it? So it's going to depend, the theta is going to depend on, excuse me, on the line that you're working with. It just happens. I kept it the same so that we, didn't have to go back over. But this is, oh, look, by the point by 60 degrees. So look at this one here, x plus 1. So this is an affine. We actually would need to talk about that. Like, well, here we go. Reflected in the line y equals 3x. Right, so this is going to give us, so what our theta is dependent on the line itself. Does that help?
Yeah.
Okay. All right. Okay, so I'm just going to keep working through here. I think I can do this in a couple different ways. I have to figure out what the projection matrix is. I can do this as projection equals 1/2 plus the reflection. Okay, so then I have to do that. I can do that is equal to 1/2. So this is 1, 0, 0, 1. We actually haven't talked about Effing Transformations yet, so I'm going to come back to this one it's a little bit later. I don't want to confuse you guys because it's really similar to the linear, but there's an extra couple steps. So I'm going to skip question 3 for a moment. Question 4 is interesting because we're reflecting a whole circle. But the important thing about the circle, I can distill it down to its center point. right? And then I'm going to reflect that center point, and then I'm going to rebuild the whole circle. So the center point is the thing that I'm really worried about, which is at -3, 2. I get that right from my equation, okay? So that's the thing I'm going to be working with. Now, this one here, theta, is what I have to figure out. So we kind of did that before, but let's do it again. I don't think I gave myself enough room when I did these. Here's my new center point, and I'm going to draw out my reflected circle. And that should be a circle. I just didn't want to draw through the -3. Okay. So far, so good. Don't worry about question 3 yet. We'll do the affine transformation in a later chapter. How are you guys doing with these?
They're okay.
Let me know if you want me to scroll up so you can see other questions. You guys have other questions you want to ask? We can leave early. You guys don't have any other questions. What do you guys think? You guys want to leave early unless anybody has any other questions? Okay, I'm going to close out the meeting. If you guys have any other questions, you're free to come to office hours and then ask me there after you've had a chance to maybe try it. And then we can talk about it in that spot. Okay. Have a great day, guys.
All right, you too.
Bye.